All right, should we get started? We have like 3 people in class. It's lovely. Oh, and nice. Get a bunch of people on the internet. Hello. So I'm just going to share my screen. Okay, so I figure what we'll do today, we're going to try to finish. This is going to be sort of awkward because there's like a bunch of people on the internet and then like 3 of you here. So if I'm not focusing on you or the computer, it's just for sort of cross-platform reasons. Okay, so we have, I would say, somewhat low ambition today. I want to show you, we're going to go through the rest of the examples that we didn't do last class. And then today we're going to talk about confidence intervals, and this will sort of lead us into hypothesis testing. We're not going to get all the way to hypothesis testing today, but yeah, we have sort of a philosophical distinction I hope we can get to by the end of class. So this is kind of a big one. This is like the precursor to the big stuff we're about to do in this class, which is regression. So regression analysis will take up essentially the last portion of the semester. Okay, so I have my I voted sticker on. You can all see that. I voted at 7:30 this morning. Okay, so let's get started. So you remember last time we talked about the empirical rule. So we have this idea that once we have the central limit theorem, when we take repeated samples, we know what the distribution is. We talked about the central limit theorem, repeated sampling, and then the distribution of the sample mean. So with the empirical rule, we have this idea about the normal distribution. And the central limit theorem gives us that the normal distribution, the sample mean, ends up following a normal distribution with standard deviation and centered on the mean, the true mean. And so we have this empirical rule where we don't have to use a computer or a calculator to check the distribution of the probabilities, whatever the probabilities might be that we're interested in. We can just know certain things about the distribution itself and the probabilities. So that's the empirical rule tells us these things, so that we've got this mass centered at the center, and then we can use this idea of normalization to sort of allow us to solve by hand certain types of problems. And the standard normal distribution will be useful later as well. So this was our normalization approach, and we sort of plotted these pictures. A normal distribution is centered on the mean with a standard deviation, and it's sort of symmetric. And then the standard normal is just we're centered on 0, and then we have this variance and standard deviation of 1. And because the variance is the squared, is standard deviation squared, variance is 1 when the standard deviation is 1. Very nice property. We call this thing Z. And so we walked through some examples. This was just sort of how we do a normalization, and some examples of what the normalization looks like, and talked about some of the interpretation. So if your standard deviation, if you're off the mean by 1 standard deviation, then that's either a -1 or a 1 z-score. And if you're off by 2, then that's +2 if it's above the mean and -2 if it's below the mean. And so the way we decided we're going to, it's a systematic approach to finding probabilities by hand when we have normal distribution. We have this 3-step approach, and I recommend you follow this whenever we're solving these things. The first step is to convert the x values into z values, which can be helpful. You can sort of skip this step, but I don't recommend you ever skip step 2, which is like drawing a picture. If we have a normal distribution, we know what the shape of the distribution is, and then we can plot the distribution. And then we sort of like write in where on the distribution we're trying to solve for, what the probabilities are. And then we can use the 1, 2, 3 rule or the empirical rule. 2 names for the same thing. So we walked through an example with 3 questions last time. So we had this idea. We had like a call center, and then phone calls coming in, and we wanted to know the wait time on the phone. And these are numbers that would drive me insane if I was actually waiting that long. So we had a mean of 18, a standard deviation of 4, and then we tried to ask 3 different types of questions. So we also know that this is normally distributed, which means we know what the distribution is, and we can just check a bunch of things. So the first question was this. So we walked through how to find that the probability that a customer waits less than 6 minutes. And so we took the question, we framed it in terms of probabilities, we set it up, and normalized it. So this was our normalization approach. We subtracted off the mean from both sides and divided by the standard deviation on both sides. And this gave us the probability that the z value is less than this thing. We know what the values are, and so we plugged those in and found the probability of that was less than some z number, which in this case is -3. From the empirical rule, we know that this number is just the value of the tail on one side. So the furthest tail, but only on one side. So this was, we know the probability in both extreme tails is 1 minus 99.7. So we know everything on the inside of z-scores positive and less than 3 is 99.7. We take the complement of that, so we take 1 minus that probability, and then we divide it by 2. And that gives us this number. And you'll remember we also did this in code. So we walked through an example in Python, and we're actually going to do some Python today. So for those of you, I think all of you have computers, we're going to get started using Python. If you don't have anything installed, that's fine. If you do have Python installed and you want to use it, you want it to use Python locally, I encourage you to do that. That's what I do. But I'm also going to show how to get started with Python in the cloud. So this really nice software from Google that is great for these kinds of applications. Not a lot of confusing installation on your computer. But just to remind ourselves where we were last time, we had example 1, and the question at hand was the probability of waiting less than 6 minutes. And we had a mean of 18 and a standard deviation of 4. And so we were wondering what the probability was that we were waiting less than 6 minutes. So what we're doing here is just taking this norm, as we talked through last time, we're taking this norm, which is essentially a function, and we're plugging in. So from norm, we're looking at the CDF. So this is just within the norm package. We're going to look at the box within the box, and we're going to take out the CDF, the cumulative density function, and we're going to ask, what's the probability that we're less than time, which we've defined as being 6? And then we need to define what the distribution looks like. And the way we do this is by plugging in mean in for mean. So this is just saying 18, and then standard deviation of 4. So this is just the variable standard deviation. We're plugging that in for 4. We can, like we talked about last time, we can call this whatever we want. So we could call this deviation, but we just need to make sure that we're referencing the right thing. So this is just, we're defining our variables like we do in mathematics. Okay, so when we run this, we get this probability. So this is 13. It's like 0.13%, which is pretty close to what we got last time using the empirical rule. And the thing I pointed out last time was that this was the empirical rule is an approximation of the truth. So if you were actually go in and calculate the z-scores, they would not be exactly 0.997. It would be, I think it's slightly larger than that. So when we actually run these things, we like to be a little more precise. But if we're doing it by hand, this is fine. Okay, so this was our first example. We walked through a couple other examples last time. So we could also ask, what's the probability customer waits more than 10 minutes? And so we could go back to our code and ask that question. And so instead of doing it directly like we did in example 1 or question 1, we could do this using z-scores. Either way we do it, it's equivalent. So let's normalize this in terms of z-scores. So we convert this question, the probability of x greater than 10, into this thing. So we just subtract off the mean divided by the standard deviation, and then we know the numbers. So we plug those in, we get this thing, simplify. So it's we found that x equal to 10 is equal to z equal to -2. So it's 2 standard deviations below the mean. And you can see this just from this number. All of this math here is just to tell us that 10 is 2 standard deviations below the mean. And so in Python, we can actually specify this. So we're specifying a z value of -2. And then we're going to plug that z value into the normal CDF. And by default, what Python does is gives us a standard normal. So if we, like we did above, Python is, we're giving it a mean and a standard deviation that are not normal, not standard normal. But if you don't specify a mean and a standard deviation, it will assume that you're asking for a standard normal. So that's what we're doing here. So this tells us the distribution, the probability all the way up to 2. So this thing is the CDF up to -2, the z value of -2. But that's the complement of what we want. We want everything above that value. So instead, we have to subtract that value off from 1, and that gives us this thing. And so we can write this mathematically here. And this is, same structure as what we did in Python. We have 1 minus the probability the z value is less than -2, which is the same thing we've written here, just in Python. Okay, so we're going to do both of these examples and a third one all together. So if you're following along on the internet, that's great. You can, either cover this tab and just hear me talk, or you can sort of split screen. If you're in the room, you have no trouble. Being in person has many benefits. So we're just going to walk through how to get started with Google Colab, which I mentioned in the announcement today. Okay, so Google Colab is just it's like an online notebook server, which is like just a fancy word for a website that lets you run code in your browser. And the way you can get there, just you could Google Colab, Google Colab, and it'll bring up this thing. And you can just click anywhere in here. You can just click on this one, and that brings up the front page of Google Colab. You can click sign up if you like. You don't actually have to pay for this. You can as a student. There's options for you. But we can just open Google Colab. And this takes us into, this is essentially running from your Google Drive. So we have this front page, and I'm already signed in, and you can see all some of the other notebooks I work with. And all we're going to do is just create a new notebook. Is this working for you all? Okay, so we'll just create a new notebook. And once we do that, it opens this thing. This is what we call a notebook. And there are a lot of nice features with notebooks. We use them pretty extensively. In fact, my entire dissertation is written in notebooks. I didn't even use Word files. It's all notebooks. So it's a very standard way of interacting with code that the industry has almost entirely moved towards. There are other ways of running code, but especially at this level and most levels, notebooks are really an excellent place. So, one thing you can do is, what I did is I named this file in class November 5. And we're just going to write some of the code I just ran, but we're going to write it in Google Colab. So you're going to have some of these examples that you can work with in your homework, because you're actually going to have to use some code. And one of the nice things here is if you ever get stuck, you can interact with Gemini, which is Google's large language model. I don't use Gemini very often, but when I have, it's worked pretty well with code. But feel free to use Gemini however you like. You will get stuck with code. It will happen. I guarantee it. And you'll get a little frustrated. And then Gemini will be able to help you out. At least hopefully. Okay, so a couple of things. You can write comments. So this hash is just, it tells Python that whatever follows it in that line is not important. Like it shouldn't run it. So this, you could write, do nothing. And then when you can click here, and that will actually execute the cell. But because it's not doing anything, then there's no actual code. It's just the comment. Then it doesn't actually run anything. But we could print anything we like. So say print, this is a test, and then you can hit enter, or the go button, and it will print it out. The other command, if you're on Mac, it's if you hit command enter or command return, it will run the cell. So below you see that it's running the cell and then giving you the output right below it. So we can do tons of fancy things. One of the powerful things with code is you can just give it logic and then it will implement it. So it's like math, but the math does the math for you. The powerful thing about it. Okay, so this is a code cell, but we can also add text cells, which is really nice. So we can call this example 1, question 1, and it'll tell you what it looks like. This is just markdown, but you can do whatever you like. So let's see. We'll send this up to the top. So this is some text telling us what's below it. If you put a hash symbol before it, this is actually markdown, telling it that it's a header. You don't have to use any of those fancy things. If you know Markdown, it's like a markup language, but you don't have to do any of those things. So this is my example 1, question 1. Okay, so what we were trying to do in question 1 was ask the probability that x is less than 6, which we said was equivalent to the probability of z being less than -3. So what we're first going to do, so we're going to import, and you can see it's giving us suggestions for what to write. Gemini behind the scenes is giving us code hints. Like we did before, we're going to import scipy.stats as from this package. We're going to import norm. So we're going to say from scipy.stats, we're going to import norm. And we can run this just to verify that Google Colab has this already installed, and it does. Okay, and then from here, we can print out norm dot, and then so it's going to bring up all of the options for us, or many of the options. One of them is CDF, so we'll click on that. And then we will put parentheses. So this is just, we're saying this is a function, so we need some parentheses, and then we can figure out what goes inside the parentheses. And so when we do that, we can see some of the things it will take. So this is one of the parameters. So here, let's just we're looking for a CDF that we're looking for the probability less than -3. So this is this thing. So all we have to do, this is a standard normal like we mentioned before. So let's put in -3 and out it comes. So this is saying the probability z is less than -3. Okay. And that's all there is to it. You can write this in fancier ways if you like, but this is powerful code, but just written very simply. Okay, any questions in the room? Can I get a temperature check on difficulty level? 3 if you're good, 2 if you're feeling comfortable, but it's new, 1 if it's very difficult.
SciPy stats, are we supposed to have that installed or something?
This thing?
Yeah.
If you're running on your computer locally, is that what you're doing?
Yeah.
Yeah, so if it's giving you an error when you run this, then you have to install the package. And you would do that. You do it pip install scipy. You just run this. So that would install using Python. But I already have it installed, so it's going to say requirement already satisfied. But if you don't have it, you can run it like that. Okay, but if you're running in Colab, you don't need to install anything locally. All right, let's do another example. So let's add another cell. So do text cell. We'll enter example 1 Q2. And then we will add another code block below. So we've already imported SciPy stats, but it's good practice to, if you're not running the whole thing, it's good practice to import it again. So for the second question, we said, what's the probability a customer waits more than 10 minutes? And we ran the normalization here. So we're looking for a probability that the z of z being greater than -2. And if you're on YouTube, if you're watching from over the internet, you can leave me comments and I'll see them on the side. So if you're having trouble on your side, just let me know. Okay, so we're looking for a z value greater than -2. And so we're just going to write this out. So this is the probability z is greater than -2. All right. And one of the crazy things, this was not true 3 years ago, and it sort of wasn't even true 2 years ago, but I wrote out the thing I'm looking for the code to write in the comment. So I wrote out this comment, which is just a statement of what I'm trying to do with the code. Gemini is smart enough that it knows how to write Python code based on the comment. And so you can see in this line below, I haven't written anything yet. This is just the code prompt, the code hint from Gemini. So this is amazing. If coders 5 years ago had this, our world would look very different. It's part of the reason coding is like fundamentally changing at the moment. This Gemini just wrote the thing for us. So if you want someone to write your homework for you, I encourage you to allow Gemini to do that. So I'm just going to hit accept. You can also hit tab and it will accept it for you. And the thing is, you have to be careful. Like you have to make sure it's actually giving you the right thing. It doesn't always give you the correct answer. So you have to just double check. But this is one of the things Excel cannot do. All right, so we hit enter and we get this number. And and it's pretty close. So again, the empirical rule is a rounding. This thing is, the code is the actual probability. Okay. So we have a third question, which we'll walk through the way we do this by hand, because you will have to do this by hand on an exam. But on your homework, you can do it both ways. So here we have a question of a customer waits more than 22 minutes. And so we write out the probability, we normalize it, we get a z value of greater than 1. We've standardized this, we've drawn the picture, and then we look for the probability. So let's go back to our code. We hit escape, which exits us out of the cell. And then we can enter a new text block. We say example 1, Q3, put in a code block below, and then we'll just import this again. You can copy paste. So it's sort of anticipating for us what we might want, but this is not actually what we're looking for. So let's write in what it is we're looking for. So this is the probability of z greater than 1. So the probability z is greater than 1. So it gives us the answer. Okay, so we'll hit enter and run this thing. So again, this is an approximation. This is the reality. And we are off to the races. You can get code hints like this using GitHub Copilot on your computer. It's just a little bit, you have to install all that stuff and run VS Code as the editor. But you can, if you have it installed on your computer like I do, you can also use Colab in the cloud. Okay, very nice. Any questions here? Nice. Let's do a couple others. So I think last time did we start this question, image download times? I think we might have made our way all the way through this. No one remembers. Okay, so we have, again, sort of another example. X is normally distributed. We have download times X is a normal random variable with a mean of mu equal to 18, a standard deviation of 5. And then we're asking the download time between these two numbers. So we can do this, just writing out the probability just like we do before. Here we're looking for the probability between two different things. We did cover this, and I showed you code last time. So we can write it out. We're normalizing. We normalize this thing. We plug in the values for the mean and sigma. And then we get that we're looking for the probability of 0, a probability of z between 0 and 1. So let's write this out again. So this is example 2, question 1. And then we'll make a code block. So this is the probability z is between 0 and 1. And so we'll just verify that the picture corresponds with the code we're looking for. So step 2, as I always recommend, in fact, when I solve these problems, I never do it without drawing a picture. So I recommend you do the same thing. So we're looking for the probability between these two things. So it's the probability of the probability all the way out to 1, but then we have to subtract off everything below 0. So this is the CDF of 1 minus the CDF of 0. And in fact, that's what the code hint is giving us here. CDF of 1 and the subtracting off the CDF of 0. So run this, and we get roughly 34%. And turns out that's roughly what we got using the handwritten approach. Okay. So let's look for another type of example. So this is question 2. So we're asked, using the same distribution, the distribution of image download times, find the X such that 16% of download times are less than X. And Gemini is going to be really good here too. Essentially what we're looking for is this value. So when you see this, it's often sort of difficult to conceptualize the type of thing we're asking for. But if you plot it out, it becomes a little bit more obvious. We're looking for where the probabilities are less than the X, such that the probabilities below that X are equal to 16%. Okay, so let's put in text. So this is example 2, question 2. And then we will import this again. You don't have to do it each time if you don't want to, but sometimes you have to import it before you run the code. And sometimes you'll load the document, load the notebook, and you won't run all the cells above it. You'll just want to run one of them. And in that case, it's better to import the package in the cell that you're actually running the thing in, instead of having to run all of them. And so that's why I import in every cell, at least in this kind of example. Okay, so we're interested in we're looking for X such that 16% of download times are less than X. And what we're going to do in the picture here is convert to a z-score. So we convert a z of 16% is on the tails of, so 16 plus 16 is 32. 32 plus 68 is 100. So we've constructed the 16% precisely because it's one of the tails of a z-score of -1. So we're going to look for a z-score of -1, and we're looking for the X value that corresponds. So the way we would convert this is we start with the z-score because we know 16% is going to be less than that, and then we convert this into a value of 13. Okay, so we can write this out. We could say what z-score gives us z a probability of 16 less than it. And so even though this is sort of bad, like the English isn't great, we still, Gemini knows what we're asking for, and so we can just tab our way in. So this is saying, from the normal distribution, we'll run this thing. Actually, this isn't exactly. That's not exactly what we're looking for. So let me bring up actually. So this is an example of when code hints don't always give you exactly what you're looking for, and part of it is like the framing of the question that I put into into the code wasn't very good. I mean, this is giving us the z value, but we would need to convert the z value back into an x value. So this is, it's spitting out a z value of something close to -1. It's spitting out something close to -1 here. But what we actually want is, so this is the z value, but we sort of already knew that from the empirical rule. What we actually want is to use the distribution itself. So the distribution of x and not the distribution of z. So what I'm going to show you next is how we can use not the z distribution, which is what we've been doing so far, but using the distribution of x. So here I've defined the mean to be 18, which corresponds with the distribution that we're looking at. So this is the distribution of x, and we have a standard deviation of 5. So we have a standard deviation of 5 and a mean of 18. And then let's just keep things simple. And actually, Gemini may be able to get this. Yes, and it does. So we've specified the mean and standard deviation, and then it's actually it knows what we're trying to do, and so it'll print this out. It may have seen the code that I had written before and then just copied it. But is it giving you the, like, when you put in the mean and standard deviation, is it giving you also the nice hint? Someone in the chat. So it's code hinting for you correctly? Nice. Okay. First off, no one ever runs like regressions, which is where we're going. No one ever does that in Excel. It's all done in code. But so coding is an incredibly powerful tool for a lot of reasons you'll see. But second off, being able to do stuff with data analytics using tools like Gemini, you just fundamentally have to know how to use code. Like, you can do it in Excel, and maybe one day Excel will have good enough features built in. But if you're trying to leverage the power of AI in your work, you just have to be able to use these things. Okay, so nice. So that gives us a value of 13, which is pretty similar to what we got using the empirical rule. Okay, so nice. So we walked through these last time, but now we're actually implementing them in code. And then we also talked about the sample mean, the distribution of the sample mean. So what we've done so far using code has only been looking at the normal distribution. So normal distribution is what the central limit theorem tells us about the standard, the sample mean. So what we're about to do is implement the sample mean using code. So like we talked about last time, we have a x bar, which is itself a random variable. When we introduced the central limit theorem, we said this thing, when we have a very large n. So x bar is the mean of all of our observations from the sample. That thing follows a normal distribution centered around the sample mean, or the mean of x bar, which is mu itself. So this thing is the mean of x bar, which the mean of an average on average is going to be the mean. So that's mu. And then we also had the standard deviation, or the variance in this case, of x bar. And that was slightly different. So when we start taking samples, we talked about the intuition. We get this sort of the extreme values are much less likely when we take the sample mean, because to get an extreme value, you need the extreme value to happen multiple times in the sample, where in the underlying distribution, you only need it to happen once. So to get an extreme value in the sample, when you have a sample size of 2, you need the extreme value to happen both times when you draw. And that's less likely than it just happening once. So the extreme values are less likely, which means we get a sort of squishing to the center when we have a sample mean. So that's why this thing, we have the n in the denominator. As n gets larger, as the sample size gets larger, the distribution of the sample mean gets tighter. And then we can do the z-score approach, the z-value approach with the sample mean as well. So if we know the distribution of the sample mean, then we can normalize into a z-value, just like we did with the normal distribution, because fundamentally the x bar is normally distributed. Okay, so let's look at another example. So let's say x itself is not normally distributed. And we do know the mean, which is 8, and the standard deviation, which is 3. We have a sample size of 36. So we want to know what the probability is that the sample mean is between these two numbers. So we don't know what the distribution is of x, but we know that the distribution of x bar, according to the central limit theorem, is normally distributed. So we have to be a little bit careful when we're constructing what we know about the distribution of x bar. The mean of x bar is the mean of x. Those two things, the mean of the sample mean is the mean. But the standard deviation is slightly different. Just like we talked about a second ago, when we start taking samples, the extreme values have to happen multiple times for an extreme value to show up in this sample. Because as the sample size gets larger, for the sample to be extreme, all of the events inside the sample have to be extreme as well. So that's less likely than any one of those events happening. So because of that, we have to normalize, or we have to adjust the standard deviation according to n. So as the sample size gets larger, we have to divide by a larger and larger value. So the standard deviation of x bar is not going to be the same standard deviation of x. So we have to divide by n. We know what n is. It's 36. I chose this number because it has a nice square root, just 6. So this thing comes out to be 1/2. So we know what the mean is and the standard deviation. And now we also, by the central limit theorem, know the distribution of x bar. So we can do all these kinds of things. So let's ask this question. So this is example 3. We're going to do it first using math, and then we'll do it in code. So first, we're stating the question: what's the probability that the x bar drawn from this distribution is between 6.5 and 9? Well, we can normalize this using the information we know. So we convert this to a z-score. We plug in the mean and the standard deviation on both sides, and then we simplify it a little bit further. So this is the probability of z greater than -3 and less than 2. That looks like this thing. So the way we do this is, we have to subtract off this value, and we have to subtract off this value. And there are a bunch of ways we could do this, but I'm going to show you one of them. So one way we can do this is we can sort of split this problem into 2 parts. We can first try to find the blue area, and then we can sort of separately try to find the yellow area. So let's just write this out. So the blue area is underlined here. So this tells us the probability of being greater than -3 and less than 0. And then this orange area, or the yellow area, is greater than 0 and less than 2. So on this interval. And then the way we can find this, this first one, so it's because the distribution is symmetric, we're looking for everything not in the tails. So we have sort of two parts, sort of two tails that are sort of both more extreme than 3. So imagine this distribution was blue all the way up to +3. That tells us the area on the inside of both -3 and +3. But we don't want that area. We want that area divided by 1/2, half of that area. So that gives us this thing. So then the second part is essentially doing the same approach, just with a 2 instead of a 3. And so we're looking at everything no further away than 2, and then we divide it by 2. So it's only the one of the halves. And we can do this because the normal distribution is symmetric. Okay. All right, so this is this value here, but we can do this with code. So let's do this using the z values. So let's go back to code. So we'll insert some text. So this is example 4. Nope, example 3. I can write code, but I can't count. So let's put some code in here. We'll copy this in. And then we're looking for the probability between -2z and 3z. And then we can just double check that this is essentially what we did. So this is another way of writing this, which is what Gemini has written for us, is to say, what's the area under +2? So that's CDF, so that should be all the way out to a z of 2. Oh, did I write this wrong? Yeah, -3 and 2. So Gemini was right and I was wrong. Very interesting. The machines are coming for us. So if you were to type in code hint this, you'd get the correct answer here. So this is everything under 2. So that's the CDF all the way out to 2. But then we have to subtract off this value. So that's this thing. This is a little harder to do using the empirical rule, but you could. A bunch of ways to do this. So we run this and we get a 97.5. So that's pretty close to what we got with the empirical rule. Okay. Any questions in the room or on the internet? All right, so let's do another one. So let's say we have x that's not normally distributed. So this is another example where we don't have a normal distribution, but we know the mu and the standard deviation. So we have a sample size of 25. So again, this is going to be a nice sample size because its square root is very nice. What's a symmetrically distributed interval around mu that includes 95% of all sample means? So we're randomly sampling, and then we're taking the mean. What's the interval around the known mu that includes 95% of all sample means. So this is essentially, we're looking for z-scores of 2 with the distribution of x bar. So we're asking about the sample means. So this must be x bar. So this is not the standard deviation we're looking at. We're going to look at the standard deviation using the sample distribution. So step 1 is to find the z-values for the known probabilities. So we know 95% of the distribution falls within 2 standard deviations of the mean. The standard deviation here is not 15. It's actually going to be slightly different. So let's calculate the upper bound. We know the standard deviation of sigma, but what we're looking for is the distribution of sigma x bar. So remember, this is the distribution of x bar. We have our center point of x bar, which is the mean of x. And then we also have sigma x bar, which is sigma, so the standard deviation of x. And then we divide that by the square root of n. So in this case, the square root of n is 5, because n is 25. So we plug all of this in. We're looking for a z-value of 2, because we're looking for 95% of the distribution. So we're looking for a z-value of 2. So we have mu plus 2 standard deviations above the sample mean, and the mean of the sample mean. And we just plug in all those numbers into this structure that we've set up using our logic from distributions. So sometimes you'll encounter sort of like plug and chug kind of math. I never recommend you just copy equations. I want you to know why we're doing it exactly this way. We're looking for roughly 95% of the distribution falls within 2 standard deviations. How do we construct 2 standard deviations above our known mean? Well, we take the standard deviation and we multiply it by 2. And then we add that to the known mean. So we're jumping 2 standard deviations up. We know the standard deviation of the sample mean is smaller than the standard deviation of the distribution itself, our sigma. And it's smaller because extreme events are less likely in the sample. Okay, so then we have this thing, and we calculate this number. All right. So so we can do the same thing on the other side, same approach, except instead of adding the 2 standard deviations, we're subtracting them off, because we have to find the lower bound. And that gives us this thing. All right. So let's do this in code. So I'm going to actually, let's see if we can just even copy this question and plug it directly. So this is example 4. Let's see if we can copy this and plug it in. Seems like it's not copying for some reason. It's probably because it's not in text format. So what's the upper and lower bound of the 95% interval when mu is 368 and sigma is, and so here we have to be a little bit careful. We have to make sure the code knows what we're what sigma we're referencing. So in this case, that's 15 divided by 5. So this thing, which is 5. So sigma is 5. So should take us through. And it does. So it's telling us to look at 2.5% of the distribution is below, and 2.5 is above. And then we'll just print these things out. And these should be this should be 3. So 62 and roughly 74. Okay. Any questions about this? Clear as mud? If you haven't worked with code before, sometimes these things can sort of just the logic of how to write this isn't intuitive. So you're going to get some chance to work with this in your homework. Okay. So the last thing we're going to do today, I want to talk briefly about confidence intervals. So we sort of just mentioned an interval like this, where 95% falls within some range. In practice, we don't always know what the mean and standard deviation of the population is. In fact, I would say rarely do we ever know this. Part of what's powerful about the central limit theorem is it allows us to take samples of any distribution and turn it into a normal. So the sample mean follows a normal distribution. But another powerful thing it does is allow us to not need to actually even know the mean and standard deviation of the population. And this is what we're about to start talking about. So we have our sample estimate, and then our the goal of what we're trying to do in general in data analysis is turn the sample estimate into some information about the population. We want to know something about the population, but we don't want to measure everything. And so what we're going to talk about for the rest of class today is how we sort of do this in practice. We talked about this maybe briefly last time, but what we do with the central limit theorem is we take essentially the sample estimate and use that in the distribution. The central limit theorem tells us X bar follows a normal distribution around the truth. What we're about to do is essentially flip this logic and talk about what we can know about the truth using the observation of X bar. We've taken a sample. What does that tell us about the truth? And this is sort of building up to hypothesis testing, which we'll get into in more detail in next class. Regression, which we are like making a beeline towards, is a way of sort of systematizing hypothesis testing in a much more structured and powerful way. Hypothesis testing, as I'm about to show you, is sort of the baby version of what we'll do in a second, probably next week. Okay, so hypothesis testing and confidence intervals. So the first thing we're going to talk about is confidence intervals. There's some sort of theory to this that's important to know, and the hypothesis testing component, which we're going to start talking about next class. But confidence intervals are tricky in a certain kind of way. There's some theory to this. So like we talked about before, we're trying to learn about the population by taking a sample of the population. We have some information about the sample, which we call summary statistics, and then we're making inferences about the population based on what we've observed about the sample. And so that's the general approach, this sampling approach, and then using this fancy mathematics we've built up over the last 150 years to be able to say a little bit more. So we have, in general, a population mean that's unknown. So we don't know the underlying distribution. We know if we take repeated samples, it will become normal. And we know repeated samples will give us a more precise estimate of the mean than just drawing one observation from the distribution. The larger the sample size, the narrower the standard deviation around the mean. We don't know what the mean is, but the distribution of the sample mean is centered around the mean. So this is all central limit theorem stuff we've been talking about for a week and a half or so. If we were to take all samples of size n, we would get the entire sample mean distribution. But if we were to do that, we would essentially be observing everything in the population, which is not exactly what we want. Instead, we want to know something about the distribution. We want to use the information we have from the central limit theorem to not need to take all of the samples and then make some inferences. So in general, we only have one sample. So in the central limit theorem picture I showed you last week, we did this thing, right? We said we have a distribution. We took I think this was 10,000 samples, and then we plotted this thing. So we know a very large sample of samples, and this thing we know follows the normal distribution. But what if instead of doing all of this sampling, we just took one thing? We took one sample. And that sample could be very large, but it was one sample. How can we know, like, what is it that we can know about the underlying parameters? So the mean of the underlying distribution, simply by taking one sample. This is what we're about to start developing. And even if you've seen this before, there's some logic to this that I think is often sort of overlooked. So I want to sort of talk about some of the nuances here, but not in so much detail. So we have one sample. We need to do something about the population parameter, so the mean, mu. And we can ask how far the population mean is from the observed sample mean. All right, so essentially, like we're observing this thing, and we're wondering where mu is in relation to it. Fundamentally, though, there's no variation in mu. Mu is known. The population of heights in the United States is fixed. There's no variability there. The variability comes from x bar. It's the mean of our sample. So when we're thinking about the variability, it's not in the mu, it's in the x bar. So, but the sort of relative position of x bar and mu can vary because we have variation coming in from x bar. So this thing can kind of move around a little bit, but it's not movement in mu. This is one of those sort of misunderstood ideas in statistics. Mu is not uncertain. Our x bar is what's uncertain, and so we need some measure of the uncertainty around x bar. All right. So yeah, lots of different places that mu could be relative to x bar. We have sort of two ideas that we're going to work with. One is the point estimates, which is really just a single number, essentially like a mean, which is mostly what we'll talk about for the next week or so. The type of estimation we've sort of examined. And then we also have this interval estimate, which example 4, where we tried to find the numbers, sort of the z-scores that got 95% of the population within them. Those are, in some sense, these upper and lower bound estimates. So we have this idea of sort of uncertainty. We call this thing a confidence interval. And this gives us some measure of sort of how precise our estimates will be. Sort of how confident are you that the estimate is correct? So let's walk through a bit of an example, and then I think we'll pick up some more of the intuition next time. Yeah, we just have a few more minutes here. But let's say we have a vending machine. So we know X is not normally distributed, and we don't actually know the underlying distribution. So we don't know the population parameters. We don't know mu, and we don't know sigma. Let's say we sample for 144 days. So our N, in this case, the sample size is 144. And then we found the mean of the sample. So this is the X bar. So the average number of things that are candy bars that are sold from the vending machine per day. And then we have variation within the sample of 60. So we might wonder, within this period, what's the probability the average number of candy bars is sold on any given day is greater than 263. And so the idea with what we're about to start working with is this idea of a sort of confidence. We fundamentally, the true parameter that we're of the distribution we're drawing from, so how many candy bars are sold on any given day, is not random. It's known, or it's fixed. The mu of the distribution that we draw from each day is not variable, but the observations themselves are variable. And so what we're trying to do is build up a confidence interval in a way that that we can get at the underlying parameter mu using our observation, our 144 observations. Okay, so we're saying, like we said before, using the empirical rule, 95% of all values of X bar are within 2 standard deviations of mu. And we've claimed this is centered on the population mean. So the distribution we're drawing from for the sample mean is around the true mean. So we have this 95% confidence interval like we did before. Now we have the terminology for it. So we can write it like this. We know some of these things, but the problem is that mu itself is unknown. So I've written this thing. This is the probability we're looking for. But the core problem is that we don't know mu. So we don't know mu. If we did, it would be simple, like the examples we did before. Conceptually simple. Here, we don't know mu. This is the problem we encounter when we look out into the world. In general, we don't know mu. So what do we do in that case? We also don't know sigma, which means we also don't know sigma X bar. So what do we do in that case? Population mean is unknown. What we do is we guess. And we have a very precise way of thinking about guessing. So I'm going to say guess, but we actually know the distribution of the guesses. So we guess. We're not going to get into the sort of theoretical detail of how we know the distribution of the guesses. But for a random sample, X bar, would be equal to, let's just say it's equal to this thing. So because we're guessing both the mean and the sigma squared, we can plug these things into the probability distribution to tell us sort of the range, the confidence interval using our guesses. So we've guessed this thing, and that's giving us a range. Okay. So I'm going to show you some pictures. This will be the last thing we do today. But is this interval actually a good guess? Like we've done this sort of trick where we said we know what the distribution is of the sample means around the true mean, which is this picture. The sample means around the true mean. And we're going to leverage the information we know about this to then put a distribution around the sample mean. This isn't saying, this distribution is not saying anything about the distribution of the sample mean directly. Sorry, it's the distribution around the true mean of our samples, or sample mean. But the center point of this distribution is not the sample we just drew, if I can say it that way. The sample we just drew is just one observation from this distribution. What's the distribution around the mean we just drew? That's the thing we're going to try to leverage, try to sort of access. So if we were to put the same distribution around our sample mean, would that be a good way of guessing the interval? And this is just a picture. So earlier we had this interval where we said we have an upper and lower bound to get 95% of the draws to be within it. And we were to run through a couple of different samples. So just some examples. And the mean in each one of these samples is slightly different. And then we constructed the bound. Let's say the mean itself was 260. So each time we sample, we get a different mean, which gives us different upper and lower bounds on our 95% confidence interval. And in 4 of the 5, the true mean, if we were to know it, would live inside that interval. But in one of those examples, it doesn't. So it turns out, this is just sort of a way of thinking about the intuition. So replacing the distribution around the true mean for the sample mean with the distribution, so we're taking that distribution, that normal distribution from the central limit theorem, and sort of like placing it over top of the sample we just drew. That trick actually gets us nearly all the way there. So I'm just going to show you a couple pictures, and then I'll let you get on. Oh, we are over time. I'm going to show you this picture, and then I've been so rude and let you force you to stay late. But we can run this kind of approach, checking if we were to know the mean, checking does this confidence interval where we essentially guess using the distribution of the sample mean, can we guess using that distribution and get a good estimate for the distribution around the sample mean? And the answer is yes. So this is the mean, the true mean, if we were to know it. These are a bunch of observations using just a sample, and then we construct the confidence interval around that sample. And the red ones are the cases where the mean is not contained within that confidence interval. And so you can see it's roughly 95%. We can run this a bunch of times, and we'll keep doing that. Keep running this a bunch of times next class. Okay, I'm sorry, I'm already over. We'll talk more about this on Thursday. Stay safe. No matter how this election goes, take care of the people around you. We're in this together. See you all on Thursday. see you all later.